Okay, so in today's video, we're going to talk about a really cool further application of the chain rule, and one that leads into our next two topics of study, which are going to be something called implicit differentiation and related rates. So let's jump right into it. So let's pretend that I got some function right here, y is equal to x squared. And if I ask you what is dy dx, well, you guys should be pretty familiar with that right now. You would say that is 2x. But what if I come down here and say what is dy dt? So all of a sudden, we've encountered something that we have not encountered before. Every time we have taken a derivative, like for example, when we did dy dx right here, what we are taking the derivative with respect to has always matched up with what our original function was a function of. So in this case, we're taking a derivative with respect to x. Well, in this function right here, y was a function of x, okay? So right now, we're going to look at how do we take the derivative with respect to, in this case, variables that are not present inside our function. So to do that, let's go to Desmos and kind of illustrate this with an animation. So if I animate this right here, this t that I'm animating right here, that stands for time, and it'll be given in what we'll call time units. R, this is the radius of a circle, and that'll be given in distance units. And this is going to be the circumference of the circle. Okay? So what you can see right here is that in this case, our radius of our circle is actually a function of t. So what we have is that our radius would look something like that, okay? Well, we know that circumference is, in this case, 2 pi r. So if I asked you to get what dc dr is, you should be able to say, oh, well, that's equal to 2 pi, okay? That's all nice and good, but that's not what we're really talking about here, because in this case, what I'm taking the derivative with respect to is what the original function was a function of. In this case, circumference is a function of radius, okay? But let's rearrange this derivative right here, and instead of asking you dc dr, let's instead ask you to find out, oops, let's get rid of that. Let's instead ask you to find out what is dc dt, okay? Well, in order to do this, we're going to need to rewrite the fact that we know r actually varies as a function of t. So this will end up being the derivative with respect to time of 2 pi times r as a function of t, which we know r as a function of t is just 2t. So this will be the derivative of 2 pi times 2t, which if we do that derivative, that's the same as the derivative of 4 pi t with respect to t, which will end up just being 4 pi. Okay, so that was a long way to go about it, but let's go about it a slightly different way. So hopefully everyone in agreement, or everyone can come to agreement that this is our answer. So if we want to just check this to make sure, what this is saying is that really this derivative is saying that for every time unit that elapses, we are changing our circumference by 4 pi. So let's stop this animation real quick, and you'll see that I got, check it out, I put 4 pi right down here, that's 12.56. If I take t, when t was 0, our circumference was 0 because our radius was 0. So therefore, at t equals 1, based on the derivative dc dt we just found, that should mean that the circumference will be equal to 4 pi, or 12.56. So if we move up to time of 1 second, there you go, we get 12.56, it matches up. At a time of 2 seconds, we should further increase our circumference by an additional 4 pi, making it 4 pi plus 4 pi, or 8 pi. So if I come down here and let's just figure out what 8 pi is, that's 25.13. So if I move this time now to 2 seconds, it should be 25.13. And once we get there, that's exactly what the circumference is, okay? So First of all, this equation works. We found how circumference changes with respect to time. But what I want to do is show you guys kind of another way to write this, okay? Let's pretend that we didn't know for a fact that our radius as a function of time was equal to 2t, okay? Let's just pretend radius was some function of time that we have no idea what it was. Okay, so let's erase this right here. And then if we go to take the derivative, we do this. So this is another application of the chain rule. So what we can do is we can take the derivative. If we know that r is a function of t, but we don't know quite what that function is, what we do is we just apply the chain rule. We take the derivative of this whole thing, and then we multiply it by what the derivative of our function r will be with respect to t. Okay? So really this is another way of saying dc dt is the same as saying dc dr. Sorry, that should be a dr. So that will be dc dr times dr dt. If you go back to the first chain rule video that I had, this is just a basic definition of the chain rule. Again, these two dr's here will cancel out and we'll just be left with dc dt. Okay? Well, dc dr, we found that before. That's just going to be 2 pi, then multiplied by dr dt. If we don't know what r is as a function of t, we can just keep this as dr dt. And there we go. And this ends up being the same answer because what was dr dt? Again, if r of t was 2t, dr dt is just going to be 2. So this would end up being 2 pi times 2, or 4 pi, the exact same answer we got before. Okay? So this brings up something, what this was an example of something called related rates. How do we use the rate of change of the radius to determine the rate of change of circumference? But we'll get into that in the next couple of videos. What's more important with this is something that I like to call the respect rule, and really it's another application of the chain rule. So if we go back to this, again, given this function y is x squared, if we want to find dy dt, that'll be the same as saying, well, that's dy dx times dx dt, which will just be 2x dx dt. Notice the similarity between this and this right here. What's the only difference? The only difference is that when we took the derivative with respect to a variable which was not present in our original function, we added this thing to the end by the chain rule. Now technically, we could apply this to this first derivative dy dx we took right here. All we would have to do is add to the end of this times dx dx, okay? But this is what I call the respect rule, okay? The reason why we don't add this at the end is, first of all, dx over dx, that's just taking something divided by itself. That's just 1. So we don't need to include that. But what you want to do is whenever you take a derivative, you look at this variable you're taking the derivative with respect to. If that is the same variable that is present in the function, I like to say, okay, I respect that function. I'm not going to add this disgusting nastiness stuff to the end of it to further complicate it. However, if we're taking the derivative with respect to a variable that does not exist in the original function, you say, I get no respect. And then you do this thing where you add this, a little bit of nastiness to the end of the function, because we say, you know what, we don't respect it in this case. The variables aren't the same, so let's just do that. So with this new concept of the respect rule, if we did dy dz, again, that would just be the derivative of our original function, 2x, and now we would multiply it by, in this case, dx dz. In both cases, what we do is we say, okay, let's just make an assumption that the function x changes with this variable t or with this variable z. But what someone is probably asking themselves right now is, well, what if x doesn't change with this variable t, or it doesn't change with z? What does that mean? Well, what that means is basically this derivative, either dx dt or dx dz right here, will be 0. So therefore the whole derivative would be 0, and that makes sense, because if this original function doesn't change at all with the variable t or the variable z, its derivative with respect to those variables should be 0. If it has no coupling with those variables, it can't possibly have a rate of change associated with those variables. So this rule still works, even if in this case dx dt or dz dt or dx dz was equal to 0. So finally, let's get crazy with our symbols here. If we ask what dy d dollar sign is, that will be 2x, the same as we had before, times dx d dollar sign. Okay, so a lot of this is really an exercise in just using a lot of different symbols, but all of this is basically just another application of the chain rule. And again, remember what I said about this respect rule. If the variable we're taking the derivative of with respect to the function is not present in the original function, we come here and we say, hey, we get no respect, and we add this thing to the end of our derivative every single time. Okay, so let's have you guys try some examples of this. So again, we went a little bit nuts with some of the symbols, but if you can take these derivatives correctly, I would say you understand the respect rule very well. So try to do these on your own, pause the video. Okay, so if you're giving the first one a shot, again, if we want to find dz dx, what we're going to have to do is first take the derivative of z with respect to y, and then the derivative of y with respect to x. So the derivative of z with respect to y, that's going to be a chain rule. That's going to be negative sine of y squared. Again, that's the derivative of the outermost thing we do, which is the cosine. Then we take the derivative of the inside, which will give us 2y. Then we look here and say, hey, you know what? Our variable that we're taking the derivative with respect to is not present in the original function, so we get no respect. So at the end, we add dy dx to the end of this, because we still need to take the variable. We assume this function y varies with x, so by the chain rule, we must add this guy to the end of that. Okay, if you weren't able to get this one, and you want to give the other one now a shot with seeing how this other one worked, give it a try. All right, so if you've tried to evaluate this next one, q is natural log of tangent of dollar sign, and we want dq d smiley. Well, again, first we're going to have to take dq d dollar sign, then multiply it by d dollar sign d smiley. So the derivative of this whole thing, again, the outermost thing we do is the natural log. So by the chain rule, this will be 1 over tangent of dollar sign. Then we multiply by the inside, which is tangent, giving us secant squared dollar sign. And then we have to take the derivative. We assume dollar sign varies with smiley. Again, what we're taking the derivative with respect to does not match a symbol that's in our original function. So we say, hey, we get no respect. And then we say times d dollar sign d smiley face. The pen is going nuts on me. Okay, that's another weird smiley, but trust me, that's a smiley. So again, if you look at these equations right here, if we happen to, instead of saying dz dx for this first one, if we said dz dy, then by the respect rule, we wouldn't add this stuff to the end. Or if we took, let's say, dq d dollar sign, we would just have everything without this stuff in the end. Okay, so notice that they're just the same. It's basically we're taking the derivative with respect to a variable that is not present in the original function. So we make the assumption that the variable, in this case y, in this case dollar sign, varies with whatever we're taking the derivative with respect to. So we add this nasty stuff to the end of it. Okay, so in the next video, we're going to look at one application of this, which is called implicit differentiation. And in the video after that, we will look at an additional application, which was similar to that kind of circle problem we looked at in Desmos, which is called related rates.